Welcome to the Grand Challenges session. We have 6 invited speakers, and the individual presentation time included 2 minutes for discussion and change over to the next speaker. We have also, as you saw, a virtual audience, so we can get a question to the speakers also from outside the room, from abroad. So the first speaker is Andrew Roberts, Some Frontiers in Rock Magnetism.
Thank you, Fabio. Thank you, Lisa. It's a real privilege to be invited to this, to give a talk in this session. I wasn't going to come this year, but this session was too much to resist. And I'm giving a single authored presentation, but really what I'm going to talk about today is results that we've been working on a long time with a lot of people, and that screen's just too far away for me to see, but you can hopefully can see who the people are. But what I want to talk about today is what I call the pseudo single domain problem. And in this paper that came out a year ago, last December, we outlined what we think is responsible for what we've been historically referring to as pseudo single domain behavior. To cut to the chase, we consider a series of manifestations to do with the vortex state. And that was really enabled by work done in our lab led by Sheng Zhao on a new set of types of fork measurements, which really provide an exceptional level of domain state diagnosticity that enables us to really pinpoint vortex type behaviors. And of course, Andy Biggin I presented this at Utrecht a year ago or more now, and Andy Biggin made the comment, well, if you want people to accept this, you need to do something about the day diagram. So with this group of co-authors, earlier this year we published a critical appraisal of the day diagram. I don't want to say more about it, except that there's 10 sets of really fundamentally limiting ambiguities to do with the day diagram. Johan Lasku and Richard Harrison have published another set of ambiguities this year. So what I wanted to do in that paper was to be more positive and say, okay, what can we do to diagnose domain state if we don't use the day diagram? And this paper by another set of people to do with the project we've been running in Japan this year in collaboration with Hiro Oda at the Geological Survey really is an evaluation, we hope an even-handed evaluation of the various methods for assessing domain state in geological materials. And really, you know, my comments at Lisa's talk yesterday, domain state diagnosis is really critical to everything we do in paleomagnetism, so we want to be able to get that right. So really that's the spirit in which that paper is offered. But I would urge you to engage with the logic presented in these papers because we think it's an important set of observations that needs to be reckoned with. So let me start just by a brief introduction on PSD behavior and what it is. This is a compilation by David Dunlop some years ago. And instead of an abrupt transition from the single domain state to the multi-domain state in terms of stability, as you might expect, instead of that, you see a gradual change with increasing particle size, which you see in multiple magnetic properties, remnants, coercivity, etc. And to describe that gradual variation, in the early 60s, Frank Stacey coined the term pseudo-single domain. And it's been recognized since the late 50s that these particles in this size range, PSD, if you want to call it that, are really critically important in paleomagnetism because so many of the particles that carry our signal are in this size range. And my difficulty with the day plot is that it really emphasizes, pushes everything into the PSD field. So this is a compilation of thousands of samples measured in the course of my career from sediments, and virtually everything's in the PSD field, not much lies outside of it. And I think that's really unfortunate because stable single domain particles are actually really common in the geological record in the samples we measure, yet we've under-recognized their importance and over-recognized PSD whilst not really understanding what PSD is. So I think those are a couple of issues. So let's go through the micromagnetics. You've all seen these images. When a particle is small enough, it's coherently magnetized with uniform alignment of moments. And then as it grows to a certain size, the moments start to flower, to diverge at the margins of the particle into the flower state. And then at some grain size threshold. These are beautiful images from Adrian Muxworthy's work, I acknowledge. There's a threshold at which a spontaneous single vortex is nucleated. And this is a fantastic micromagnetic mechanism for minimizing the surface energy, because the magnetization just curls around that vortex core beautifully to reduce the magnetic energy of the particle. And as you further increase size, domain walls start to nucleate off the wings of that vortex core along certain crystallographic orientations. And Wynne Williams was the pioneer of micromagnetism in our field, and doesn't get enough recognition for how widely important those phenomena are, in my view. But if you look at various other early micromagnetic presentations, this is from Carl Fabian, this one's from Lisa, double vortices were pretty commonly reported back in those days too. So the state of the issue is pretty nicely summarized in 2002 by two divergent papers, one led by Lisa, one by David Dunlop, where Lisa said that the vortex state represents the PSD state quite nicely, thank you very much. And I don't think that paper gets enough recognition for pushing the field forward. And David in the same year said that exotic structures like spin vortices are an unlikely explanation, and that you need separate SD and MD-like moments. And I would say history will side with Lisa rather than David on this, but David's argument has held sway for an awful long time. And these are giants of our field. We like and respect them. But I think Lisa was right and David was wrong on this occasion. So if you go and, so where we come from in our group is we've been working a lot on fork diagrams. Some people might glaze over at that, but for us, forks are a fantastic tool for looking at the micromagnetic state of your assemblage of magnetic particles. And I could show various representations. I think Adrian and David's is the best early representation of this, because they were on well-controlled particle sizes. And so in this right-hand one, the characteristic behavior of PSD particles is that you get a divergence of these contours. Single domain grains have a central ridge or closed contours around the origin. If they're interacting, they spread. But when you get into the so-called PSD state, these contours diverge, and the distribution diverges onto the vertical axis. And then, whoops, as you get coarser, they diverge further until they become vertical for very coarse particles. This is a more recent fork diagram for so-called PSD particles from Johan Lascu and colleagues' paper. They call this a pirate hat distribution. It has three corners and a tall peak. And they argue that this is characteristic of a multi-vortex state, and I'll talk more about that in a minute. So these fork diagrams are what we get for bulk measurements. And so you might say, well, okay, that's what PSD looks like. If you know what you're talking about with regards to forks and vortices, you'll say, well, this is what a vortex state fork diagram looks like, Andrew. It looks nothing like what you're talking about. You get these upper and lower lobes, and this secondary butterfly feature, as it's called. What gives? So if you look at a hysteron type representation, as we're used to using for illustrative purposes, you get switching from saturation at a single field and to negative saturation, and then up switching at a positive field, which gives rise to a single peak on your fork distribution here. If you use more realistic particle response for Stoner-Wolfart-like particles, where the easy axis is not necessarily aligned with the applied field, you get a more complex response. You still get this central point, but you get negative here and a positive in between them. So that's a classic single domain, non-interacting single domain type response. What you get on the right-hand side here is it's again a highly schematized version of a vortex type response, but what you get is you come from positive saturation, you nucleate a vortex, then you annihilate it at strong negative fields as you come to negative saturation. Then as you ramp the field in the other way, you nucleate the vortex and annihilate it again, coming to positive saturation, and that gives rise to these two peaks that you see here. And if you study the figure here, you can very easily see how these switching fields produce distributions in those areas. And then if the coercivity of these particles is somewhat lower, those loops become narrower and the distributions push towards the vertical axis on the diagram. So again, you might say, well, that looks nothing like the reality of geological samples, Andrew, what are you on about? Very few geological samples show this, and you would be right. So if we look at iron nanodots, which are very precisely controlled particle sizes, on the left-hand side we have 52 nanometers, so these nanodots are in the single domain size range. You see this lovely central ridge and the negative here, as you expect for uniaxial particles. And then as you go from 52 to 58 nanometers, you spontaneously nucleate these vortices that give rise to these upper and lower distributions with this butterfly feature. And as it grows further, you see those features separate more. Well, again, this is material science, very precisely controlled materials. In the earth sciences, we don't have rocks that do that very often. So this is an example of a bacterially produced, a thermophilic bacteria produced magnetite that produces hexagonal plates, very thin plates, and you can see the particle sizes vary over several hundreds of nanometers. So this is a very nicely controlled particle size range in the vortex state, and you can see that the raw fork diagram produces these upper and negative lobes, but of course they're smeared over large nucleation annihilation field distributions because of the particle size distribution. So we're almost always dealing with distributed particle sizes in what we do, so that's what we're seeing. You can ignore this middle panel. The right-hand panel is a new type of fork measurement that I talked about, pioneered by my friend Sheng Zhao in our lab, and you see these upper and lower peaks appearing, which is a manifestation in a transient fork diagram of vortex state behavior. So this is a very special geological sample. What happens in normal geological samples? This is the type of PSD-like fork response that we get. If you look at the transient fork for that, it's just like what I just showed you for those bacterial magnetites, where you get these distributions of nucleation annihilation fields in the transient fork with these contours closing in on each other in the upper and lower parts. A multi-domain sample behaves entirely differently, where it's more vertical, and it stays more vertical with these wing-like features, which are distinctively different from these lobes in the vortex state behavior. So you see very clear differences in the manifestations of the micromagnetic behavior in these fork diagrams. So the most comprehensive analysis that's been now done of the vortex state in geological materials comes from the Cambridge group. Johan Lascu led this work. He talked about it at Utrecht last year as well. And it's a very nice piece of work. And what you see, this is a single vortex sample. You come from saturation. And what they've done is traced various switching fields and returns. And these are the corresponding vortex states in each part of these respective simulations that they've plotted. And what you see is, just as we expect, this upper and lower hemisphere peak plus one on a central ridge response here. So that's a single vortex response. What do you get for a multiple vortex response? With focused ion beam nanotomography, what they've done is produce this really complex geometry. It's an obsidian that cooled while it was moving, so you get this complicated particle morphology. But what you can see in green is the multiple vortex cores that are being micromagnetically modeled by the mesh around that particle that's been identified, the dimensions of which have been identified using focused ion beam nanotomography. And of course, computationally, this is demanding to do. It's only a single sample, but they've mapped the switching field distributions in these various forks, and it gets a little messy. You see various responses here, and that's represented here by comparison with the pirate hat response for the bulk material, right? So you can see that this area is starting to be filled in by this micromagnetic model for this material, but what we need is a more comprehensive micromagnetic model that does multiple particles, etc. It's just computationally too difficult, but you can see that it's giving rise to this response. So how many of us have seen fork diagrams like this in the samples that we've measured? We see them all the time. And these authors would argue this is a characteristic signal of the multi-vortex state. And so many, many, many of our samples are dominated by the multi-vortex state, for which we yet to have a proper theory for how it might behave for paleointensity, for example. And I just, in closing minutes, want to run through a couple of other examples that have been published in the last year. This is from the IRM group, led, I guess, by Bruce Moskowitz, where they've used Merrill to do the micromagnetic modeling. You can see single vortices, double vortices, and they've got calculated MFM diagrams, magnetic force microscopy, and experimental, and they're showing the presence of single double vortices in these intermediate titanmagnetites. The first reports of vortices in intermediate titanmagnetites in exactly the size range where you expect vortex behavior. In electron holography, you see vortex behavior every time you look at particles in that size range. And I want to close with what I think should be compulsory reading for us if we want to understand the vortex state. This is a paper that was published in Nature last year. You don't often see methods type papers published in Nature, but the reason it was is because they were able to identify long theorized micromagnetic states that have never been observed. And so what they do here is they have a sample that's bombarded with an X-ray beam, and they use the XMCD technique, X-ray magnetic circular dichroism, where you have right circularly polarized light and left circularly polarized light, and you take a difference image, and you can get at the magnetic structure, and they can invert that to get a three-dimensional magnetic tomography of the magnetic state within this stub, which is 5 microns across and probably 20 microns long. And the imaging that you get is absolutely stunning. So this is a cross-section through this stub. You see single vortex states like this, and you see where everything curls around the core, and you see anti-vortices where everything curls away from the core. And what you see here is, I can't see the arrows from here, but I think that that's a counterclockwise vortex. Here you have a clockwise vortex. Here you have two vortices with the same vorticity, and between them is joined by what's called an anti-vortex, this guy, where the spins diverge away from each other. And this line that joins this chain of vortices in this multi-vortex material is called a cross-tie wall, and where you get a vortex abutting against a domain wall, you get a thing called a block point, which is a singularity where magnetic order is completely destroyed, okay? So I'm now using a set of language that is unknown in our field. Why? Because we've not been using the techniques. This is a very new technique, it's fair to say, but because we've been flying blind by using techniques that don't give us the imagery at the scale that you need to really understand what's going on. So I would say that as a grand challenge, we sit at a really exciting stage in rock magnetism and paleomagnetism, which derives from it, because we have the opportunity to replace a tired phenomenology with a modern understanding, and we have the tools. We haven't valued micromagnetics enough, and it's really great to see a resurgence in our respect for what we can learn from that. So we have Merrill, we have Forks, we have slice and view fib, we have X-ray vector tomography, and I would say as a challenge to us, let's work out the reality. And please stop using the word PSD.
Thank you, Andrew. We have time for questions. And before, if we have a question from, no?
Are there online questions?
No.
Questions for Andy? Brendan?
I guess my main question with a lot of these methods is it's very hard to directly do this on the samples that you're actually going to be using in your experiments, right? You can pre-select the same rock, but if you're looking for things that, for example, a single domain, then they're going to be quite heterogeneous because that particle size is very small.
So the question is, in abbreviated form, how do you get these analyses on the samples you're running, and how do you deal with that? And I think the Cambridge group is a great example where they go and they do focus ion beam nanotopography. They look at the sample, they map all the magnetic particles in it, and then they micromagnetically mesh them, and they get the response from those particles. So I think it is possible exactly on the samples you measure. But I think synthetics are a good way to get started on this.
I'll add to Brendan's question, and that is that if we're measuring it for paleomagnetism, like trying to do intensity or something, then by doing the fork or the imaging, you destroy the magnetic signal, the remnants, and so you can't do it. You can't do forks on exactly the same specimens that you did paleointensity on. So how do you get around that?
Not sure. I think we need a couple of years of really working on the background to demonstrate the fundamentals of how the vortex and the single vortex, multi-vortex state works, so that we have a much better refined fork or other representation of how they work, so that by analogy you can say, okay, this fork diagram is telling us that. And I think we're close to that, actually. You know, you don't like dealing with sister samples because you want to know exactly what, you want to measure the rock magnetism on exactly the sample you measured, and then once you've heated it, it's changed. So I would say sister samples, but I know you don't like that. And I understand your reasons, and they are good, yeah.
Thank you. Next speaker is Susan McEnroe. The rule of atomic scale properties on magnetic anomalies at different scale, local, regional, and satellite. Yes.
Where do I change?
This is the link, so you have to use this one.
Okay.
Try. It's working.
I hope so. Okay, well, thank you very much for the invitation. I was requested to talk on this subject. It's very broad, it's large. I'm going to try to give some examples of large-scale anomalies, locals, information from satellites. And if I don't get through the talk, just see me afterwards and I'll show you the rest of it. There's a picture of a large eclogite body in western Norway. This is one of the most well-exposed regions of ultra-high pressure rocks in the world, and that will be an area I'll discuss in the talk. This talk has a lot of contributors through it, my students as well as workers I've been involved with in a number of years. This is the World Magnetic Anomaly Map, and this is a wonderful time to be working in anomalies because we not only have all this abundant data from everything from drones to satellites, but we also have people working on compiling this data together. And this is an enormous amount of work because you have to get everything to the same elevation. You have to bring all these large data sets in. So we not only have a huge amount of data, we also have great people working with this, and it's a wonderful time then to start thinking about what are the sources of some of our magnetization. So there are some things when we think about anomalies, we do think also a bit about in paleomagnetism, and that is that the Earth's field has a direction, and it also has an intensity, and that intensity varies a huge amount around the globe. And we can see here from 20,000 nanoteslas, it gets up to 65,000 nanoteslas. Your magnetic anomaly is reacting to the strength of the field as well as where that magnetization was acquired. So of course your anomaly will be very different for the same rock body depending where you are on Earth. So we have to think a little bit about our different components in our anomalies, and this seems very basic. We have NRM components and we have induced magnetization. What do we have to think about with NRM? Well, basically, we have an inclination, we have a declination, and we have a length of the vector. The length of the vector is the strength of the Earth's field. That's where your body acquired its magnetization at the time it blocked. This will be your NRM contribution, which then, of course, can be later modified. Or it could not be modified, very much depending on the coercivity of it. We also have to realize that statistically we're working with vectors. We cannot do scalar statistics. You have to do vector statistics on your studies. Coherency of the NRM. You can calculate your Königsberg ratio, your Q values, but you really should be you have to do these in a vector Q value. So when you think of this ratio of the NRM to the induced magnetization, if it's less than 0.5, we're pretty safe working with induced magnetization and modeling the field at that point. If it's higher than that, as the NRM becomes more and more important, we have to know those directional components. And this is really more challenging than one would think. You can have large studies, but are these representative of the area? So simply, if your Q is 2, it means your NRM is twice as large. So you still have your other unknowns, geometry, depth to body, and different aspects. But if you have a good set of vectors that you can use from here, you can get an adequately good model. One other thing is the age of the anomaly isn't necessarily the age of the rock body. It's something we really need to think about more. So when we're dealing with induced magnetization, this is simply the response of the rock at the present field at that location. Your intensity of the field could be 20,000 nanoteslas, it could be 60,000 nanoteslas. The geometry of it, you know exactly. You're right there. Of course, if you're working in a regional area, then you have to do some averaging too of looking at how you want to deal with your inducing vector. But generally, when it's an induced anomaly, you're much more able to work with that data to model, but you also need to think about what the statistics are around it. The other aspect is that anomaly is very closely related to the present-day field. So the anomaly is a response of your magnetic properties in a weak field, and this is actually very challenging. The NRM is not straightforward. Understanding the nature of NRM and the components of it are difficult, and we run most of our rock magnet experiments at high fields. I'm just simply showing here a study in southwest Sweden where you can see that most of the anomalies along the coast there are what we would call negative anomalies. These are dominated by a remnants. This is close to -60, and you can see in the stereo net an absolutely remarkable coherence. That's NRM data. In the right, we're just showing the mineralogy that's carrying it, which is a titanohematite that's highly exsolved. This is just to visualize what we're talking about with Q values. On the upper panel there, we have Q values of 0.2, 0.5, and the total magnetization is very close to the inducing magnetization. In the middle and lower panels, as our NRM component becomes more important, you can see how the total magnetization is deviated from the induced magnetization, and you absolutely cannot model these bodies without having a relatively good idea of your direction of remnants. So the other aspect we have to think of is what is the material property of what we're measuring? What's the material property of the rock? And so you could have different magnetic structures, everything from paramagnetic, ferrimagnetic, AF, abundance of oxides, your domain states, microstructures, interfaces, atomic arrangement at the interfaces. All of these are playing a role. Does your samples demagnetize at 5 milliteslas, 100 milliteslas? We look a lot at coherency there. Then, of course, when we go deeper into the crust, we have to think of the blocking temperatures of our main solid solutions as well as our main minerals, because we will lose remnants as we reach these temperatures. One of the interesting things with what they're doing with the new satellite data now is, of course, they can try to make a global magnetic thickness model. And this is based on the seismic, using seismics to do thickness. The best fit is using a susceptibility of about 0.6. Now, having looked at databases that have more than 100,000 or more samples in them, I'll tell you that less than 10% has that susceptibility. This is very interesting. It's something we need to think about. So I want to move now to northern Norway, where we're going to look at thinking about deeper in the crust, where we're going to look at some ultramafic rocks. Again, this is a diagram made from a compilation of data. Again, NOAA puts out wonderful data sets that we can work with. One thing to see here is just the difference between looking at a 5-kilometer and a 4-kilometer elevation, and how defined the definition of the anomalies change. Remember, magnetism decays with the cubic root. The deeper you go, the broader your anomalies, the less definition you're going to pick up. It's not changing. So we want to go way up in northern Norway, and we want to go here because we're going to look at the roots of a deep plumbing system, and we're going to be looking at ultramafic rocks in the area. And here, the exposure is absolutely fantastic. That's dunite being cut by pyroxenite dikes. We have kilometers of dunite, webstrite, wirbelite to look at. We also have samples that are very unaltered, in addition to samples that aren't. But one of the key features here I want you to look at is most of the data set, excluding the gneiss and the gabbro, has a Q value above 1. So we're very interested in finding out what the source of the magnetization. The diagram on the right, where we're plotting the ultramafic rocks, where we're plotting density, you can look at the effect of serpentinization. On the far left, where you see densities of 2.8, we're looking at heavily serpentinized rocks. On the far right, we're seeing rocks with densities of around 3.4 or more. These rocks are virtually or completely unaltered. What's interesting, what we see here, is a large range in their magnetic properties. And so we want to know what they are. One way to do this, of course, is we look at thin sections. We absolutely make sure our thin sections are unaltered, but we can also make magnetic maps of our thin sections. And so here you're looking at 3 different anomalies over grains, and we can look at the direction of the anomalies, the coherence of the anomalies, but we also can now go and say this is where we want to go onto the SEM, TM, or wherever and start looking at this material. We can also take that data and look at the analytical signal, which will then center you directly over the anomaly, of the source of the anomaly. And so when we have a large grain, you can see there are actually areas that are more magnetic than others. What Gertje found, and Zueda working together on this, is the main carrier is a chrome spinel. It's a primary magnetic material, and where these show anomalies, there's X solution. This X solution is going towards the iron end member, which is magnetite. We believe this is the primary magnetic mineral that crystallized and dissolved during cooling. And so in these dunites, we actually feel we've identified the primary source of magnetization. Now we want to go to the very deeply subducted rocks in the western gneiss region, because here we can look at the effects of magnetic changes when rocks have been down to depths of 100, maybe even 200 kilometers, and then returned, because this might tell us something about conditions of stability of oxide phases deeper in the crust. Traditionally, it was considered that when you get to high pressure, eclogite facies rocks, you no longer have a magnetization, because basically you're reacting out to make garnet, the iron from the magnetite. That's true in the eclogite. The eclogite facies rocks have been to those conditions. The reason they're not eclogite has to do with the availability of fluid. As you can see from the PT diagram, almost all of these rocks have been subducted more than 100 kilometers, some of them as high as 200. The high pressure are in the coesite area, the ultra high pressure are from the diamond region. It's very interesting. Most of the rocks, 1,500 samples there, they're magnetic. There's a range in magnetism that we find, some of them relatively weakly magnetic, some of them much strongly magnetic. So there's certainly a magnetic response. What are these minerals? This is what we're seeing. It's a variety of oxides, from magnetite, ilmenite, to titanohematite and hemoilmenite. What's very interesting is the microstructures and the textures we're seeing in these rocks are completely different from what we see in regular igneous rocks. And there's a lot of symplectites, a lot of oxides made on the return. This isn't changing very fast. That's slow. And the lower right-hand corner there, you're actually looking at an eclogite myelinite, and the oxides in it are hemoilmenite and magnetite. Now for a very local case, this is a classically studied area, the Black Hill Norite in Australia. And here we have a mixed mineralogy. We have magnetite with exsolution of ilmenite. We also have ilmenite with an exsolution texture in there. That is actually reduction exsolution of magnetite. And so this is, I haven't seen this very often. I'm seeing it now in a few more studies we've looked into. But the FO2 conditions become very important. So in the same rock, we can have oxidation exsolution, and we can have reduction exsolution. And again, this is just a thin section map over the sample where we've identified where the anomalies are, and all the oxides are outlined there by black outline. One of the interesting is the silicates aren't showing any response, which I'll talk about in a bit. So this is another intrusion, a gabbro, very large anomaly in Australia, remnant anomaly. And again, high NRMs, average of 32, high susceptibility. And here, we really have this mixed mineralogy, oxy-exolved magnetite, reduction exsolution of magnetite and ilmenite. So we've studied the phase relations for this. By studying anomalies, we're studying phase relationships now and how you can develop these microtextures. I'm just putting in this slide here from the Bushfield when we're looking at plagioclase and discrete oxides. And the anomalies here, so I just want to point out, is the single domain magnetite and the plagioclase. We're picking up a very weak signal. This is actually very true for all the other plagioclase from Black Hill Norite we've worked with. And I think the statistics that we have to think about. There's just some fork diagrams showing what you're looking at in the plagioclase separates on the right. I want to end this to look at the Bjorkum-Sakandal intrusion, because I always have to go back there. It's an incredible layered intrusion with incredible different magnetizations that we see, with a very huge remnant anomaly, which we've been trying to understand the nature of this. And I hope soon we will understand that. There's a lot of variation in oxides here. The remnant oxides are hemoilmenite. There's a lot of multi-domain magnetite, and you can see by the susceptibility plots on the top, there's a variation in susceptibility from the early part of the intrusion. In the later part, where magnetite's on the cotectic, this also is true. You can see it with the density. The real deviation is NRM. So we need to understand what's the nature of our very efficient NRM carrier. And that's in this one unit here, primarily where we're looking at a norite with orthopyroxene, plagioclase, hemoilmenite, magnetite. And you can see many of the Q values here of these studies are more than 10, NRM 10 times higher. So we go to the thin section, this time a slice, and we can map. We can do chemical maps, we can do magnetic maps, we can take the analytical signal, we can identify the sources. We can actually then also, we have these oriented, so we can look at what are the anomalies, where they are, what's the orientation. We know the NRM, we can map the top and bottom, and then we can start modeling. We can go in and model what is the anomaly over those individual grains, what are the properties we need to use it. We can then take that and we can go to the TEM. We can start to look at what's the phase carrying the magnetization. We're still doing much more work on this. Falco's actually working on this now. We have also found one lamellae of magnetite in here. Dominantly, we've found hematite, ilmenite, but we really can't explain it completely with that. Orientation is also another very important factor. When you're in the hemoilmenite, magnetite, in the hematite, ilmenite, or hemoilmenite system, if you're being magnetized parallel to the basal plane, you're going to have a much weaker NRM than if you're along perpendicular. If you're perpendicular to it, will be much weaker than if you're parallel to it. That intensity varies by an order of magnitude. Another aspect is that we've been working with is what we call the efficiency of magnetization. Why are some microstructures, some phases, much more efficient at a weak field, acquiring a weak field NRM? Not a high field, but a weak field NRM. What are the parameters around that? So by studying anomalies, we've also done a lot of work back with looking at phase diagrams, looking at interface magnetism, looking at antiphase domain boundaries, looking at exchange bias. All of this is the result of studying anomalies. What are the sources of the anomalies? So in many senses, it's very much a circle. The source of the anomaly is a mineral, and that mineral has many interesting properties. Depending on the microtextures, domain states, we have different anomalies. The last thing I'm going to show is that we now visualize this different. Whoops, can we start that? then you just ask your grad student, or he offers to visualize your data for you. So now we're at the Bjerkum-Sakendal, and we're actually going through the anomaly, seeing how these anomalies change, and we're no longer deceived with those little magnetic highs on the surface, but we can really visualize our data. And I think this is something that's also going to help us a great deal with working on our materials and identifying where we can go and sample. And this is something Alex, he just asked me if I'd like a movie, and he gave it to me a half hour later, which was pretty terrific. So thank you very much.
Thank you, Susan. Any question from the virtual audience? No? Okay, from the room. First question.
So hard to see out here.
Familiar with the, I think it was David Clark paper back in '96 from Australia, where he advocated for a magnetic petrological classification system with all the work that you're kind of doing, correlating it with petrology. Do you think that'd be one of the end goals? Be actually like creating a whole,
Yeah, I think one of the other great things is what's happening at CSIRO, and we're getting remnant databases. I really wish MAGIC, I don't know how much we have NRM values in there. People, please publish your NRM values. A lot of people, Paleomag papers, everybody's interested in that demagnetized vector. And the NRM is something we desperately want.
More questions? Out there.
Well, yeah, so that's actually a good point. So if you want to think about something like the Western Gneiss region, when those rocks were actually at 200 kilometers, or possibly 100 kilometers, the microstructures, you have to go back to the PT path. There's part of it in which you're actually below, it's relatively cool. You're below 600 degrees. So it's a function of temperature. Once we get up to a certain temperature, your microstructures, of course, are going to go back into a single phase. And so these are all microstructure developed on the abduction, on the return path, but exactly pinpointing where this is for the different systems. One thing that's very interesting, in the hematite-ilmenite system, we don't see any embayments. We see very clear grain boundaries, where we do a lot in magnetite-ilmenite, showing that these two systems behave extremely different, and the hematite-ilmenite is much more stable at those temperatures and pressures.
Okay, thank you. Thank you very much. Oh, sorry. Next speaker is Les Nudge, beyond the single model and single domain, using big data to answer fundamental questions in rock mag.
Do you have a
yes. Pointer? You have a pointer here.
Okay, thank you very much for inviting me to give the union talk. So I'm going to be discussing what happens in our grains as we look at the evolution of grains as a function of geometry and size. And I'm particularly going to focus on the blocking temperature. So how thermally stable are these things? From a micromagnetic perspective. So we're really trying to reconstruct what real samples do, real paleomagnetic samples, how they behave from the ground up. How do I change that? Oh, it's the... Yeah. Okay. Oh, no problem. Yeah. So on Monday, Wynne was giving a talk about what happens in equidimensional iron, and it's really a lot more complicated than that. The picture that emerged there was quite complicated already, but in reality, we have to consider the effects of geometries, applied fields, and different mineralogies. In this talk, I'm going to just concentrate primarily on what happens as a function of different geometries. Then at the end, I'll make just a quick aside on how we deal with applied fields. And the other problem is that we end up with a huge number of possible solutions. So we're interested in trying to make this problem tractable somehow. So first I'll take a look at blocking temperatures and what do we know about blocking temperatures already, and how can we scale up our methods to include things like elongations. So how does micromagnetics actually fit into all this? So you begin with a real core sample, which is the thing that you see on the left, and we model that as a collection of geometric remnants carriers. So these are our magnetite grains or whatever mineral you've got in there that's carrying your remnants. Obviously, this is not to scale. Otherwise, you wouldn't actually see the grains. It's just an illustration, but one of those grains, you can see what the actual magnetic structure of the grain looks like, and it's the thing on the right there. So how do we actually go about calculating the blocking temperatures? So for any given temperature, we select we take a collection of geometries for any given size, for any given size, elongation, and we give it an initial random magnetic field, and we try to minimize what the possible local energy minimum states are given those initial randomizations, random states. And what we're really trying to do here is we're trying to map out what the possible local energy minima are for one particular grain size. Once we do that, we have to calculate an energy barrier. And in order to calculate an energy barrier, what we have to do is pick two good states. So what do we mean by good states? What we mean is a magnetic structure that has a small Gibbs free energy. So this is the total energy of the grain, which is a function of the demagnetizing field, the exchange interaction, and the magnetocrystalline interaction. And also, if you have an applied field. So we simplify that, and then we look for for magnetic structures that have small angles between the vortexes. So we represent vortexes as these isosurfaces, and they really kind of bring out the circular structure of the vortex. And we also make sure that the chirality, so the handedness of each magnetization structure is the same. So in order to do an NEB, or a nudged elastic band minimum energy path calculation, this is kind of an illustration of how it works. The real problem is very high dimensional. This is just a two-dimensional surface. So these 2 points at the end there, where the little elastic band is anchored, those represent the LEM states between which we want to calculate the minimum transition path, or the path of least action. And what you'll see there is as the path evolves, I've plotted just a simple example function of what the total action is. And you'll see that the band passes through a saddle point, which it doesn't pass through the actual hump in the middle, it kind of goes around. So when we calculate the minimum action paths, oops. After we calculate the minimum action paths, if we take the energy points for each structure along that path, we end up with an energy barrier. And what that energy, so each point on this graph here, as the grey bar moves along, represents an intermediate point between the transition from one LEM state to another LEM state. And if we take the size of that energy barrier, we can calculate what the transition energy is between one state and another, and we can use Néel's equation to calculate the relaxation time for a given temperature. And once we have a bunch of relaxation times, what we can do is that for any given relaxation time, so we classically use 100 seconds as lab time, we can see where the graph of temperature versus relaxation time crosses, and we pick that point as our blocking temperature. So in previous work, so in a previous study, we looked at the evolution of the blocking temperature as a function of grain size. So what you're looking at here is the graph that Lisa presented yesterday. So we have the size of the grain. So this is one cuboctahedral geometry. And what we're doing is we're increasing the size of that cuboctahedron, and we're looking at how that affects the blocking temperature of that cuboctahedron. So two surprising things emerge. The first surprising thing that emerges is this region here that tells us that these single vortex states in cuboctahedra are incredibly stable. The thing on the left here is also relatively stable. So this is the single domain transitioning up towards the flower state that Andrew was talking about earlier. The really surprising thing is this thing in the middle, where the transition from the stable single domain to the stable single vortex goes through this unstable region, which Lisa refers to as the bad boys. So Valdez-Grijalva looked at Gregite, and what you're looking at here is not blocking temperature, it's relaxation time as a function of grain size, because he didn't have all the material parameters available to him for the full temperature range of Gregite. But what you see in the middle here is, again, this unstable region. And it's clearly affected by the geometry of the grain. So he picked several different cuboctahedral type geometries, and he looked at how the relaxation time and the blocking volume evolved as a function of grain geometry and size. So again, we see an unstable region in Gregite. And on Monday, this is the graph from our iron paper. Again, you see the unstable region. It's very small. It only really occurs in the cubic iron grains. And it's better illustrated by the Polaire diagrams. So this first curve here, begins here. This first curve, this 30 nanometer curve, is extremely stable. It's flowering. Then we go through this unstable region. And after the unstable region, we have these nice, stable vortices that give us these nice, high blocking temperatures. But what happens as we elongate the grain? Clearly, there's some dependence on shape. So how can we study that? Well, one of the things that we can do is we can take a geometry and we can just stretch it out and squeeze it and see what happens. So if we do that, we end up with a lot of models. We looked at elongate. So in this particular set of data, which is just finished, so we've just finished running these, this set of data, we looked at elongations from 0, so equidimensional, to 100%. That's a 2-to-1 aspect ratio of the grain. So we were stretching them out. We were increasing their sizes, and we mapped out the domain structures as a function of temperature all the way up to the Curie point. And for each temperature, size, elongation, we do 50 initial random starts. So those initial random starts that I was alluding to earlier, and we end up with a very, very large number of models. So first of all, how do we deal with that complexity? But before we even look at that, let's consider what we can just pull out of the data that we have, which is incredibly surprising. So what we're seeing here is a 100 nanometer grain at a fixed temperature, and I'm just stretching it out. And you can see that the vortex core, it begins aligned along an easy axis. As the grain stretches, it the grain, it kind of pulls the grain along to some intermediate 110 axis, and only when you get to 85% elongation do you see that it switches to an orientation along the axis of elongation, which is really surprising if you consider what happens in a single domain model where you only need these tiny elongations to get something that looks like uniaxial shape anisotropy. It's very surprising that you have to take the vortices and really stretch them out in order to get something that might be stable. So how can we go about reducing the complexity? Remember that we've got about 2 million models in there, and that's just the beginning. That's just one geometry. One thing that we can do is we can calculate some useful numbers, some useful metrics for each of our little magnetization fields. The first thing that we can calculate is the helicity. So this is the handedness. So this is basically going to tell us which direction, left or right-handed, the vortex is twisting. The next thing that we can calculate is this SVAC or SVAC value. It's a bit contrived, the acronym, but it's a quantity that tells you the distance of the vortex core with respect to orientation from its nearest easy axis. And this is a really nice thing to calculate. So as you can see, it's based on the magnetic crystal and anisotropy energy, but I just take out the temperature-dependent value. So I've just got something that's purely directional. It's really nice because what it does is it classifies different types of structure. So something that's pointing along one axis, if you have another structure that's pointing anti-parallel to it, it sees them as being the same, which is the right thing to do if we consider the Gibbs free energy. So the Gibbs free energy is another calculation that we perform. So that's just comes out of the micromagnetics, and it's just the sum of the exchange, the Zeeman or the external field, the magnetic crystalline anisotropy, and the demagnetizing field. And the last quantity that we can calculate is the net remnants. So this is the dipole, essentially, that represents this structure. So it's a nice directional measurement. So it tells us exactly what direction this thing is pointing in. So once we calculate these, what can we do for a size? So remember, we're working on from the geometry, so the elongation, size, a temperature cluster, and within those clusters, we've got 50 geometries. So how can we choose 2 or more, possibly more, endpoints for our NEB calculation? Well, we can use the previous quantities that we've calculated, and we can start to do some clustering. So what I've done here is I've used some hierarchical clustering. So first I look at the helicity, and this really splits the graph nicely into 2. So what you can see on the left are red, and those are left-handed, and on the right you see all, the red ones are left-handed, the right ones are right-handed. And if we then take that branch, so this is just the blue right-handed helicity branch, we can look at the SVAC value. So you've got 2 clusters here. You can't really see it on the screen, but you've got 2 clusters here, and within each of these clusters, they're pointing in opposite directions to each other, but the SVAC value for them is the same, so they're the same type of structure. And finally, we can actually just pick out the individual directions. So if we look at this final branch, what we see are 3 structures that you saw previously. So these 3 structures, but just taken from 4 different perspectives. So we can tease out which structures from our 50 are the same. And once we pick out which ones are the same, we can, so these 4 will be the same structure. These 8 will be the same structure. These 4 will be the same structure. These 3 are the same structure. And so what we can then do is calculate all the energy barriers between the different pairs. So 3 pairs, 2 pairs, and one final pair, which gives us 6 pairs in total. So we can calculate the energy barriers between those. And once we have the energy barriers, we can calculate these rate matrices. And from the rate matrices, we can then, so we assume a Markov process between all of the different transitions, so between all of those 6 transitions. Once we have the transition matrix, that gives us the probability of transitioning from one structure to another in continuous time. And then that allows us to do all kinds of cool things like calculate the net remnants as a function of temperature and time and how the thing evolves in time. So it gives us all this interesting stuff. And finally, so Carl works out in his paper that we can add a small correction to our zero field solutions so we can calculate what the effect of an external field is. So finally, what we intend to do is build a huge database of micromagnetic models. So what would be really cool is if we can put real samples in, so the stuff that Ian and Richard are doing, those amazing little models, they would be perfect for this. The stuff that Greg's doing, we could put that in the database, so he's looking at the titanomagnetites. And what would be really great is if we could build a huge database of structures and blocking temperatures with the aim of going backwards, so trying to answer the previous point that was made. How can we understand what's going on inside the grain? Well, maybe we can do the inverse problem. So is it possible to look at what the magnetic signature of a grain is and try to figure out what's actually inside? And that's the end.
Thank you. Have we question from the online platform? No? From the room? Okay. Can you use, please, the microphone, because we are recording?
That's really great stuff, Les. So my question is really, you don't have to go very much bigger in size or complexity of geometry before you start getting hundreds and thousands of different LEM states that are accessible. So have you got any ideas how we can best bridge the gap between this kind of approach, where you have a sort of a tractable number of states, and the sort of more complex geometries where we suddenly have to calculate millions of energy barriers potentially?
So the answer is no. It's incredibly difficult as the number of states explodes. You have to do the right thing, you have to calculate the energy barriers between them all. What you can do, so the poster that you were presenting on Monday, what you can do is make some nice assumptions about the sizes of the energy barriers. Just by looking at just the Gibbs energy of the 2 grains. So you can assume from one transition, at least from the lower energy state to the upper energy state, the best possible scenario is that you'll just follow the path up. But the problem is what happens on the way down. So if you're trapped in one of these high energy states, is there an energy barrier? And that energy barrier could be really small. So we don't know what the energy barrier is to go from a high state to a low state. So, yeah, it's a very difficult problem. More simulations. That's my answer.
Thank you.
Thank you.
We have to move on to being scheduled. Next speaker is Katie Constable, using paleomagnetic data to characterize global geomagnetic field behavior over the last 2 million years.
So we're going to have a slight change of scale. I have to say that I'm really quite intimidated by the technical expertise that people are now showing in rock magnetism, and what I'm going to talk about is really quite simplistic by comparison. I'd like to thank the organizers for the opportunity to talk about this. I'm going to talk about global magnetic field behavior over 0 to 2 million years. And the work that I'm going to talk about is essentially about various modeling things that have been carried on by myself and lots of collaborators who are represented here. The work has been made possible really by activities involving assembling very large data sets which are now accessible to the community at large. So I could have talked about all kinds of models, that many of which you will have heard about already in this meeting, but I'm instead going to focus on the ones that I've been involved in, because I think that their limitations are not dissimilar to what else we see in the other modeling things that people are talking about, even with new data and new strategies such as Bayesian algorithms and introducing covariance structures in the modeling. So with that, let me just start all this out by a little preamble where I ask, why is the magnetic field important? Is there still a grand challenge here in trying to reconstruct it in the past? And I'm going to argue that there is, through illustrating the work that we've done and showing you a few interesting features in the models that we've been dealing with, mostly related to geomagnetic spikes and excursions and the limitations of the models that I'm going to show you in actually being able to image these things. And so that will then lead me to the end of the talk, where I'll talk about what we really don't know. The magnetic field is really important to us. It basically protects us from the solar wind and magnetic storms. It, of course, originates in the core of the Earth here, produces a largely dipolar field, and that presents an energy barrier that holds off the solar wind. It helps preserve the Earth's atmosphere, and the high field strength we have today may be important to technological uses. It may also be important in the origin and evolution of life. That's something that I still don't think we understand fully. Lots of people and various biological life forms use the magnetic field for navigation, orientation, and location. And of course, there are many earth science applications, ranging from plate tectonics, studies of reversals. Here's an early reversal record. To magnetostratigraphy. Here you see the reversal timescale, and the use in actually accessing Earth's history and evolution. So I'm focusing on the past 2 million years because that's more accessible and we have more data. But really what we would like to do is to study global long-term field variations, and there have been in some of the other sessions some talks about how long the dynamo has subsisted. But in looking at the long-term field variations, I want to identify here basically 3 strategies for looking at the field. Firstly is computer simulations of the physics of Earth's core, so geodynamo simulations. And we know that we don't manage to do those yet in the right regime. There are also direct measurements which span this interval here. What you're looking at on the right here is the spectrum of variations in the axial dipole moment. And I'm going to talk about, and this spectrum is derived from some of the models that I'm going to talk about. Explicitly, I'm going to talk about PADM 2M, which is an axial dipole moment variation for the past 2 million years. A new model that's just coming out called GGF 100K that spans the last 100,000 years. And then some of the Holocene models, CALIS 10K.2. So if we want to look in the intermediate regime between this piece of the spectrum, which is representing the historical record for the past few hundred years, and the magnetostratigraphic timescale, which is back here in the reversal and reversal rate changes, we're talking about using archaeological artifacts and rocks as magnetometers. And if we were going to use numerical simulations, we would know everything, and that would be great, but then we could produce very detailed field descriptions, but they have limitations, and we need these observations for comparisons. So if we were looking at the field today, we'd look at data from satellites, the latest of which is SWARM, and from observatories, and build a field model that might look something like this. This is one that Suzanne showed. This is the field strength from 6 months of swarm data in the middle of as of June 2014. And you see here that there are these characteristic lobe structures. There's a South Atlantic anomaly where the field is very low. And if we look at the change in the Earth's magnetic field over a 6-month period, we see this dominant hemispheric asymmetry. These are basically spherical harmonic models, and these provide a mathematical representation of any magnetic field component at the Earth's surface. So we could compute d, I, declination, inclination, field strength, and so forth. And if we have time-varying models, we can produce snapshot maps, or time series at any location, or animations of what the field's doing over time. So if we look closer at the swarm model, this is from a recent paper by Terry Sabaka and others, we can go down and look at what's going on at the core mantle boundary, and this would be what the radial field structure looks like at the core mantle boundary in the top panel here. You see those lobes at the Earth's surface have become much more detailed near the core mantle boundary. The South Atlantic anomaly has resolved into several patches of reverse flux in the southern hemisphere, and this is a nice and detailed model, but of course we're not going to be able to do that with the paleomagnetic observations. But there are some questions we could ask, and they are something, so here are a handful of them. What causes those flux lobes? Are they always there? Are they locked in position? No spoiler here, of course, they're not, as many of you already know. Is there hemispherical asymmetry in the rates of change as we see in the modern field? How rapidly does the field change, and will it reverse soon? And I'll argue that we can't really answer this first question yet. I would say it doesn't. If we knew how rapidly it changed, we might be able to answer the second of these things. Personally, I'm thinking we're okay for the time being. And then the next thing would be how high can the field go, and can the high values be sustained for a long period of time, or would they then lead to a collapse in the field? And how long does an excursion or a reversal last, which we heard a little bit about this morning in terms of very short and rapid changes. So these are the magnetometers we have for the past field. We have lava flows and sediments and archaeological artifacts. And if we are thinking about million-year timescales, I'm going to start with the longest timescale because it's what we have the least detail about in terms of time variations. This is the kind of data distribution we have. If you look on here, you'll see the black things are lava flows, the brown things are archaeological things, and the triangles represent sediment records for a couple of million years timescales, and this is actually an outdated database at this time, so I guess we could remake this model, but we haven't yet done that. And we made from this these are all intensity measurements, or relative intensity measurements that were subsequently calibrated in work that was done by Leah Ziegler, using the absolute intensity measurements to calibrate the relative paleointensities. If we look at the data distribution for 100,000 years, the thing to carry away here, again, we have sediments, marine and lake sediments in here, archaeological artifacts and lava flows. And the main thing to carry away from this impression as an impression of the data distribution is that we have regions where we have a lot of data, and some of them are internally consistent. And then we have other places where we have very few observations, and there was a nice example this morning from Brazil where we discovered that in fact it's the data from Argentina and new data from Brazil seem to be mutually incompatible, which is something that we have to live with in some of these observations because we don't have detailed understanding of the magnetization of all of these proxy magnetometers. Okay, so this just tells you a little bit about age control. I put this up here because this is a figure that shows all the different kinds of age control that go into the 100,000-year database, and the mean sedimentation rate, which is something we have to take account of in our modeling because the sedimentation rate leads to smoothing, differences lead to smoothing in the record. And one of the key limitations in what we're doing here is a lack of detailed knowledge about age control of the individual observations that we have. So we have observations as a function of time or age. We don't necessarily know that age well enough. And if you look at the temporal distribution, you see that this is for the 100,000-year data set, you see that as you move towards the present day, there are many more observations than there are in the distant past. And this is actually a common feature on all three timescales that I'm going to show you the results for, that in the individual databases, there are more data as you move towards the modern day. So if we look at these data sets that are compiled, and many other people have started to do this as well, we can then recover a measure of axial dipole variations as a function of time, starting on the 2 million year period down at the bottom here. This is the record that the model that Leah Ziegler produced. We call it PADM2M for paleomagnetic axial dipole moment for 2 million years. And you see in here that there's a range of intensity variation. There are several features that we know and love, and a couple of things. I will just draw your attention to the fact that if we look in the Bruns, before the Bruns-Matayama reversal, the average field strength is lower than it is for the current epoch, and by about 25%. And that seems to be a robust result, no matter what you believe the value to be. Because the value here would depend on how you do the calibration. If you look in the next level up, we're looking at an expansion from this dashed line this is the past 100,000 years. And you see in here the axial dipole moment variations for the past 100,000 years. The most impressive feature in here is the Lechamp excursion, which I will argue is the only excursion that we see in this model that is actually a global event. And if you look in the top here, then you're seeing an expansion for the past 10,000 years. Here are two different Holocene models, one from Sanja Panofska's methodology, one from the CalS methodology, and then you also see the tiny little bit that we have from the direct observations. And one of the things I want to draw your attention to here, because I want to talk a bit more about it, is the position of the geomagnetic spike that has been observed in the Levantine region, and how it's really not that remarkable a feature in terms of the axial dipole moment, but it does occur at a time when the dipole moment seems to be rising. So if we, just to sort of summarize some things I'm going to say in here, the historical field, there's a decay in the modern field, which is driven by Western Hemisphere activity. If we look in the Holocene, the dipole moment ranges from 60 to 100 zeta amp meter squared. There are local field spikes not reflected in the dipole moment to 200 zeta amp meter squared, and these seem to be associated with growth in the dipole moment. We have a strategy now for looking at a property we call the Paleosecular Variation Activity Index. It's a measure of not just directional departure from the axial dipole, but also the field strength, and if it goes larger than 0.5, we believe it could correspond to an excursion, so that by more standard measures. And the current PSV activity is rather low, and during the Lechamp it is extremely high. We can measure this locally or regionally or globally, and that makes it an interesting strategy for looking at whether things are occurring globally or locally. And then another feature that I'll note from these field models is that in the 2 million year model, the average decay rates are slower than the growth rates. Okay, so this is the Paleosecular Variation Activity Index as measured from the observations, and this is the global measure. This is the Northern Hemisphere in blue and Southern Hemisphere in red, and the Atlantic Hemisphere versus the Pacific Hemisphere, again in blue and red. And what you see in here is that the activity index, so I said before that when it goes above 0.5, we think that we've got something that would be excursional. You see in here that the Lechamp excursion comes booming out, not much else does. And then you also see that it comes at different times and different strengths in the different regions of the Earth, and that in the Atlantic Hemisphere it's much more pronounced than it is in the Pacific Hemisphere. And there are some good reasons why that might be, partly because of some limitations in the data. You also see that some of this temporal variation and when things are peaking in the activity index, we don't really have very good control over because of age controls in the sediments, which are we would prefer were better constrained. What we do see is that the duration of the Lechamp excursion varies with with location. You see here a variety of different locations across the Earth. The average is 1,300 years, minimum of 350, maximum of 3,000. That's a reflection of both, I think, variability in the length of the excursion by our measure and also the recording medium. So with these models, we can actually make a very detailed prediction of what's going on in the field just about anywhere, and you see that in here. This is actually an animation which I'm not going to show you for lack of time, but just draw your attention to the fact that we can look at the field strength here, the activity index, the radial field at the core mantle boundary, VDM if that's your preferred unit, and then also where the VGP paths would be concentrated for that particular instant in time, and then we can look at how other things are evolving. And I'll just show you here, so this, we can look at these animations, but I won't allow you to because I don't have time. And I'll just highlight here a snapshot of what the field looks like actually at the center of the Lechamp excursion. You see the activity index is very excited. We also see that the VGP paths are going all over the place. We see there's a very low field strength in here, and we can start to think about what's happening in terms of where things are going on the core mantle boundary in terms of flux patches on the surface of the core. Thank you. So going now, the other feature I wanted to talk about was the geomagnetic spike. Here's a paper, snapshot from a paper by Ron Shah et al. In 2016. And you see here these spikes in geomagnetic field behavior. And I want to just briefly highlight what they look like in our models. This is a slightly broader view of a spike where we've taken data from Magia and looked in various geographic bins. This is the actual region of the Levant where it's most pronounced. If we look at now at the 10,000-year model, this is would be an animation of that, which you're also not going to be allowed to look at. And I can show you, but we can look at how the field evolves over time. If I look then at what this looks like at the time of the spike, what we see in here is there's this flux concentration beneath, loosely speaking, beneath the Middle East. It actually seems to be associated with this little blip in the dipole moment that I showed you earlier. And it very rapidly melds with what's going on in the high latitude flux lobes here. So these are some real, we don't see much going on. If you look at the overall intensity at the surface of the Earth, we are not able to resolve what's going on in terms of the actual fitting the observations. And I should have highlighted that here, where you can see that the field model CALIS 10K.2, if you look at the VADM, which ought to be being predicted by our model, you see that it doesn't achieve anything like the high values in this spike in here. So I will skip this slide. So I will just say now that some of the experiments that Chris Davis and I have done and work with Monica Corto, we've seen that the rates of change for spikes are really hard to establish because of regional inconsistencies. But they have to have a broad footprint on the Earth's surface. And if we think about the remaining challenges in building these kinds of models, I've highlighted already the geographic coverage, the need for consistent age controls. We want reliable uncertainty estimates in both the data and the age control. And the final thing that I will say is that I think that in order to be successful in actually explaining what's going on in more detail in the regional models, we need to develop new parameterizations for building these models beyond the spherical harmonics, where we look at models with local support so that we can actually blend global and regional models in order to exploit the data coverage that we do have. Thank you.
Thank you. Have we questions? Online questions? No. Questions from the room? I cannot see. Ah, there is a question. Okay.
Online? Sorry. Short. What are the magnitudes of spatial prediction uncertainties associated with the global maps shown in your presentation?
Very large, I think would be the correct answer. So we have The ways in which we assess those uncertainties, they of course depend on what particular element you're looking at. If you look at the declination, inclination, and intensity uncertainties in the observations, they tend to be of the order of 5 to 10 degrees in terms of directions, and they are between 5 and sort of 30 microteslas in terms of the paleointensities. When we make these maps, the predictions in the northern hemisphere are probably good, I would say, to, in the intensity maps, probably to within 5 to 10 microteslas. In the southern hemisphere, there are regions where we have no observations, and therefore the uncertainties are much larger.
Okay, next speaker is Rob Coe. What we know and don't know about reversals.
Yeah. Well, hello. Oh, I think I have all the controls that I need, maybe even more. So thank you very much for coming, and thanks for the invitation. I'm going to talk about reversals, but in particular the behavior of the transitional geomagnetic field, and this is from paleomagnetic evidence. Really nothing about geodynamo modeling. And I have lots of reasons to be pretty optimistic from what I've heard at this meeting especially, that we may pretty soon come to what we want, which is a global picture of what's going on during a reversal. The reversals, they take a blink of the eye to occur, and so they're really hard to resolve. But there's really some quite amazing advances being made, and I think we'll be able to improve on what we know quite a lot in the next 5 or 10 years. So what do we need? We need trustworthy, high-resolution paleomagnetic records. That's what it's all about. Sedimentary records. They're the ones that can give us a continuous record. They're widespread so that we have a chance of getting global coverage, but they're also a lot trickier to interpret. Then we've got volcanic sections, which have the advantage of giving generally accurate snapshots of what the field direction really was in a very short period of time. But there definitely are too few of them to ever hope to get good global coverage or even global coverage. They're suitable for absolute paleointensity, which is a great advantage. Then how would one proceed? I'll concentrate on the first few reversals, and in this talk, mainly I'll concentrate on the most recent reversal. Then find and evaluate these high-resolution records, and that's where a lot of the work comes, and comparisons and questioning your own interpretations. And then finally, invert the best of these records for a particular reversal. So our thinking about what happens during a reversal have evolved immensely over the past 50 years, 60 years, that what happens during a reversal has been investigated. Here on the left, we have the classic lava flow record of Van Zyl. It's a 180-million-year-old volcanics from a flood basalt. And you can see that the record seems to have some detail in it. It's a very old record. We'll never find other really good records of it anywhere, so we can't deal with it globally. And also this particular record that you're looking at right now was contaminated quite a lot by lightning, because way back in 1963 they didn't have a whole lot of, in fact they didn't use any AF demagnetization on that study. On the right, we have the classic sedimentary record of Minkovich et al. You can see 3 reversals, the last 3 reversals, nicely in the record. I should say that both of these records showed one very important thing, but it's only illustrated in the right-hand one, and that is that the intensity of the field decays during a reversal. It decays a lot. And this is true of all reversals and all or most excursions that have ever been described. But there's very little transitional detail in this record. It's a slow sedimentation rate. On the right below, we see another lava flow record of successive reversals from Kauai. These are these are 4 to 5 million years old. You can see they don't have the greatest detail, but they're interesting because they were successive reversals. So the first reversal was from normal to reverse. These are showing directions, not VGPs. And the succeeding reversal was the opposite way. And the intriguing thing here was, and still is, that they look kind of like a movie run forward or backwards. The paths are on top of each other. And for instance, if you had a field that stood still while the dipole decayed, you could explain having successive reversals like this. And on the left, then, we also have successive reversals in lower Miocene sediments. So these two are from Crete, so they're from the same place. Now the paths don't coincide in this model, in this record. And so the standing field model wouldn't work, and we need something more complicated, like a flooding model, for instance, if you remember some of the models that Ken Hoffman discussed a long time ago. But the important thing about this sedimentary record is that you see that the VGP paths are confined. So there's a bunch of jitter, which I would think might actually be due to problems with the resolution of the sediments. But then the paths themselves are quite confined. So this is a question that we'll investigate all through the rest of this talk. What do the reversal transitions really look like? Yes, so this repeats what I was going to say. Oh, yes, and remind myself that there's a poster of new work on these Kauai works by Bogue and Zhang tomorrow afternoon, where you can learn about intensity variation. I can go very quickly through this slide just to say that how do you define how long a reversal transition takes? If you use the directional record, all the estimates that have been made for quite a long time, they zero in on an average of 5 or 6 or 7,000 years. Whether you look at a lot of older data or if you winnow it for a higher sedimentation rate records, that's what you see. But that's for the last, that's for the what you might call the final flip. And actually, we'll see that some reversal records can be much more prolonged than that, the period of instability. So those were from the early 80s, and there were many records from the 70s that showed sediment records like the ones that I showed in the slide before last, confined paths. And then comes along this record of early Miocene basalts in Steens Mountain, Oregon, which are beginning to show a lot of complexity in the paths, if you like, of the VGPs. Not to go through them all, but you can see that it moves from reverse to transitional to temporary normal, then back to transitional, and then back to reversed. And in this intermediate period, the field intensity falls greatly. In the temporary normal that it doesn't hold, the field intensity recovers quite a lot. So that's from the Oregon Plateau. And then just to jump ahead, since it's the only place to do it, the record as it now stands from the work of Nick Jarboe is he's spliced in some more records of the same reversal from sections in the same area, but up to 60 or 80 kilometers away. And one now sees that the transition path is anything but longitudinally confined. In fact, it covers most of the globe. But we have these records from higher sedimentation rate cores, classic records, from the 90s, with sedimentation rates of 4 and 6 centimeters per year. And one sees that they're still longitudinally very confined. They're from, one is from the equator in the Atlantic, one is from the North Atlantic. And they're also different from each other. So they can't be dipole dominated, but they're very, very simple. So if you thought of the dipole field decaying away and something like the non-dipole field remaining, how does one get such longitudinally confined paths? Whereas the Steens path that I showed you before, it really reminds one of what might happen if the field disappeared and you had a much more rapidly and spatially varying non-dipole field producing the transitional directions. So, you know, what goes? There seems to be a conflict. Maybe the Steens record is just an oddball from back sometime or other, and these ones of the last reversal are good descriptions for the last reversal. But that was began to be resolved in the late 90s when finally some very detailed records of the last reversal came in from deep sea cores, in this case from the North Atlantic, that were showing really rather complex VGP paths that are beginning to cover a lot of the globe, like the Steens Mountain much earlier reversal. And these are in sediments that are deposited 2 or 3 times faster than the previous records that we saw. And with this, are there other reversal records that show this? Well, there was a record published from the Searles Lake core of the Gauss-Matsuyama reversal a couple of million years earlier, which also showed quite some complexity. Then along comes sedimentary records, which complicate the way we think about the last reversal some more, the arrival of the precursor. And basically, what was discovered from 2 cores originally in the Western Pacific equatorial waters was that there are, besides the dip in the intensity just before the reversal occurred, we have a prior dip in the intensity that is maybe 12 or 15,000 years earlier. And, well, I won't get into the beryllium-10 signal here in this particular case, since it's done on this different reversal. But this was one of the early uses of beryllium-10, cosmogenic nuclide, to also try to understand reversals. And just to talk very briefly more about beryllium-10, this study by Vallée et al. Yeah, I should look at this record here, the screen in front of me. It's easier to see. What you see on the left is a record of the intensity during a reversal in the bottom path and the reversal angle, the change in direction in the top path. And then you see that the peak in the beryllium-10 in the sediment coincides extremely well, basically exactly, with the change in direction and also with the minimum in intensity, as it should from what we know about how these form. On the right, they're offset by 20 centimeters, and the reversal record lies 20 centimeters below the beryllium-10 record. And this is a good signal of averaging or remagnetization of the transitional record. Not too much, but some. Then very briefly, since those were just two records from the North Atlantic in 2017, paper by Channel et al. Now added 4 more sites. These were the ones you saw before. And these 4 sites also from the North Atlantic with even higher sedimentation rate and ages agreeing with what we think is the age of the Matsuyama-Bruns reversal from many points of view. And just to show one of those site records, on the left you see the U-channel records of the reversals, and on the right you see discrete samples. I should have pointed out in the previous one of 983 and 984, there were these 3 places where, just in the pull-through records, where it seemed like there was concentration of VGPs. And we also see those in the discrete samples, which is reassuring since there's a lot of questions about how much smoothing and how much the record gets altered by the smoothing from using U-channel and continuously pulling it through a cryogenic magnetometer. There's basic agreement in the discrete sample record, except it's not perfect because if you look carefully, the discrete record arrives first at 2 and then goes to 1 and then goes to 3. And if you undo this tangle, you find that it's not exactly the same. So there's still some things that need to be cleaned up about these records. But they're great improvements on the past. And it's a good argument for doing discrete sampling on anything that you really want to try to use to resolve reversal records. One of the reasons for my optimism is there's now a lot of new argon dates that are applied to fragments of the volcanic records that we do have for the last reversal. And there's a poster tomorrow afternoon by Singer et al. Where you can look at these results in detail. Briefly, there's 5, 6, 7 places where these results have been, these lava flow records have been now dated more accurately with multi-collector spectrometers. The 2 records on the left and the right are the most detailed. On the left, from Tahiti, from one of the Tahitian sections, there you can see that there are 4 reversals, and actually there's another one in there. There are 4 reversals in the directional record within a very short period of time, maybe 5,000 or 10,000 years, around 790 in the precursor area. And here on the Haleakala record, this is all the time just leading up to the last flip to normal. And you can see, I have a few more minutes left, is that right? What's that? Oh, okay, I thought you were going to do this at 5 minutes, sorry. So we see there are, what shall we say? The Bruns-Matsuyama period of instability is 22 to 28,000 years long, and there are many, many quick flips to be resolved. The VGP paths are not, they're not longitudinally confined, but there does seem to be a pattern to these records. There's 2 studies actually that have produced these more dates, one by Balbus et al., it's already published, and one by Singer et al., it's in press. And as I say at the bottom there, I'll leave you to examine these correlations and lack thereof in the poster yesterday. But here are the dated clusters of lava flow records versus time. And then here are sedimentary records and their VGP latitudes. And here are sedimentary records and field intensity. And the thing that I would point out is there's considerable agreement and disagreement, but there's more correspondence between what happens in the lavas and their temporal equivalence in the intensity. It looks like we're still losing quite a bit of the directional complexity out of the sedimentary records. I was going to say that lake sediments, they can be wonderful. Here's from Mono Lake, 3 records 10 kilometers apart that are virtually identical, and DMAGs that look as good as the stalagmite records that we saw this morning, so they can be very good. As was discussed this morning as well, we hoped for a while that the Italian record was the answer to our prayers for the Matsuyama Bruns, but it has the problem of having way too old an age, as well as, even for me, too fast a directional change. And it's interesting that the same kind of model that Muxworthy and Evans have suggested is the explanation for that record, we actually have seen happen at one locality in Mono Lake, published in this 1994 paper by Coe and Litticoat, where the strong field following the first half of the Mono Lake excursion has wiped out these black dot directions. They've remagnetized it. So finally, then when we get good records, what do we do with them? Well, then we can invert them. A favorite of mine is the Leonhardt and Fabian inversion technique. And we don't need an infinite number of records because the magnetic field satisfies Laplace's equation, and so 4 or 5 good records spread over hemispheres will work. And I'll leave you to read these, but a global solution is really the holy grail of this, and they will enable us to do a whole lot of stuff, including inform dynamo models so that we can really begin to home in on what dynamo models are Earth-like. Thank you very much. I'm sorry for the taking too long.
Thank you. We have no time for questions, but if you have online question, or if you want to make a question, you can use the platform. It will be forwarded to the presenter. Next speaker is Trond Torsvik, Phanerozoic Earth History, a journey in time and space from base to top.
So how do I operate?
Yes, it's a PC. Okay, I think you can use this one.
Okay, with the arrows.
Yes.
It's the pointer. Okay, thank you for inviting me. And I guess my talk will be different from all of them. And the time scale will be the entire Phanerozoic for the last 541 million years. I didn't prepare a specific slide of problems, challenges, because that will probably take my whole talk. So I will just mention them as they go along. Of course, we have different reconstruction methods we can use. I'm mostly going to start with Paleomagnetism in the beginning, a little about history as well, but just on the lower part here, what kind of reference frames can we use? So we use global moving hotspot reference frame back to 83.5 million years, and if you want a challenge, be aware that I'm a plume lover. There are people who doesn't even believe in plumes, so then you can forget his reference frame altogether. So that means you cannot say a word about absolute reconstructions. So you're left with Paleomag, but that's of course has a longitude problem, which we have been looking into. But if you now, I will focus on the Indo-Atlantic domain, so we use this global, we can also use a moving hotspot reference frame. It's not global any longer, back to 120. Then we use Paleomag, and apart from the longitude problem, we also have aspects of true polar wander if you want to connect it with a moving hotspot, because that's insensitive to true polar wander, then you have to correct for it. And just, and some people don't believe in true polar wander either, so just to give you another, even though it's happening right now at 10 centimeter per year on our dear planet, people rejected it ever happened in the past. So obviously we have some challenges. So maybe the message is maybe we should start talking to each other in the future. So I'll go to, there. Okay, I thought I'd make a little history of Paleomag, at least but the first ever polar wander part ever made was back in 1954, which was about 3 years before I was born. And I think one of these gentlemen is still alive, Ken Craer, if, I don't know, I haven't heard that he's passed away. And that's an interesting polar wander part. It was called a polar wander part of Europe. Of course, they were all in Cambridge. It's actually a polar wander part of Britain, and I will show you it. There are some problems with that. But they noticed that if they look at older poles, they call them Devonian and Permian Silurian on here, it deviated from the present-day pole. So they actually concluded that this is true polar wander. It's actually the spin axis changes relative to the solid Earth. Just 2 years later, 56, Runcorn also got a polar wander bar from North America. Here is plotted as a north polar, and he noticed these parts were slightly off in longitude, and he said they might have been together once upon a time, but the modern North Atlantic had opened and split them apart. So then it was not true polar wander any longer. This was continental drift. So this is more or less the first geophysical evidence for continental drift. So we are still here. We only, in the tree revolution in earth science, we still haven't been to the seafloor spreading and plate tectonics, so Paleomag was very instrumental in leading us to plate tectonics in the end. Okay, of course, there was big problems. Here's this polar wander part from 1954, just to see the challenge they had, because some of the poles were from southern England, that's in red here, that was part of what we call Avalonia. Some poles were part of Scotland, which was Laurentia, and of course they didn't know there was an ocean between them in the good old days. It's called the Iapetus Ocean, so they just combined these things. And they called it Europe, but remember, Avalonia was part of Gondwana, Africa, once upon a time, and so it wasn't even a representative for Europe. So you mix two continents which had nothing to do with Europe. Let's say you go back in Cambrian and Precambrian. So my professor used, Brian Sturt, he used to say, you can be right for the wrong reason. So this really pioneering Polo Wonder part doesn't even look like some of the new ones. So this is one of our new ones. I'm not going to go in detail. Another challenge, I would say, I've heard a lovely talk, and there's a lot of happening in rock magnetics and so forth, but practically nothing in Paleomag. I'm a compiler making Polo Wonder part, and if I find 5, 10 poles a year of good quality, that's it. Maybe it's only a few. So we are not really going anywhere trying to do global plate reconstruction because nobody's doing Paleomag. Maybe it's boring, we don't get funding to do it. It has to be something more sophisticated. So that's a big challenge. So I want some of you maybe to do something else as well. And just a little about the methodology when we do global reconstruction. Of course, we can combine them when we know what we call Laurentia collided with Baltic and this Avalonia at about 425. Then we can combine these Polo Wonder parts. And so we have relative fits, we combine them. We can do a similar from Gondwana for the last 500 and 550 to simplify these things. And ultimately, we also want to go global to do this, making global parts. And some of the things we do, I'll come back, we rotate them actually all to South Africa by a relative plate circus. That can do back to Pangea time. Problem is to go beyond it. And for the younger times, I use moving hotspot reference frame to about 83, I said, and then for the Indo-Atlantic back to 120, and then we merged it into a hybrid reference frame. So we try to do an absolute plate tectonic since Pangea assembly. That's about 320 million years. So this is something we started about a decade ago. And of course, it's all about longitude. And I always make the joke, longitude is something totally artificial. The Brits got it through Greenwich, and I said the French got a meter in Paris. But of course, it's a total artificial thing. You cannot determine longitude in a celestial manner. And of course, everyone who's done Paleomag 101 knows you cannot do longitude, but it's a very easy trick, it's a dirty trick. If you can make a global Polo Wonder part and rotate them to the continent you think have moved the least in longitude, the most stable, then you have some sort of a quasi-stationary global part. And when you do that, then things becomes much easier, also in terms of analyze true Polo Wonder. So, for instance, you don't want to make a Polo Wonder part in North American coordinates. I know it's popular in America, but that's one of your worst ones, because it's moved a lot in longitude. Or India, for instance, but Africa is a good candidate. Europe is not too bad either. So what we do then when we make these things, we compile all the parliamentary data, again, very depressing. We have a database of about 25,000. In my latest compilation, I picked 600 and I killed the rest. So we need more good, high-quality data. We rotate them all to South Africa now, and then we can use a spherical spline, so running mean, we make them global Polo Wonder part, and then to make reconstructions, then we use this part, and we rotate, we reconstruct South Africa then in an absolute sense, and reconstruct all the others relative. And if we're going to merge this lower part here now with a moving hotspot reference frame, we also have to correct these for true Polo Wonder, and I think it's very simple. If somebody doesn't believe in true Polo Wonder, I'm happy to sit down and explain how we do it. Simply, you take this reconstruction, you're looking for some coherent motion of all the continents, let's say over a 5-10 million year period, and that pole better be on equator theoretically, and we can define various times when it's rotating clockwise, anti-clockwise. Very simple. So this is a very strong message. People are now arguing, some like true Polo Wonder, some don't. It's a mixture in these things. A Polo Wonder part is a mixture of relative or continental drift and true Polo Wonder. Of course, some people have very large true Polo Wonder. Mine are, from this kind of analysis, they never exceed 10 centimeter per year, actually the value you have today. Be aware that 10 centimeter value today, almost half of it is actually deglaciation. So actually global warming is actually generated almost half the signal of true polar wonder you see today. And the rest is change in subduction sound through time. So by doing that, of course, I said we rotate everything to Africa and assume there's no longitude change. We know from a global hospital reference frame there are some longitude change. So we use that in the younger time. And then we just keep this some sort of semi-stable. And then we can actually make movies like this. So this is actually, this is in a mantle reference frame where we correct with true polar wonder. And you can see these, the equator here in red is the Paleomagnetic equator. So you can see now it was very little true polar wonder and it's kind of rotating back and forth. And so this is what it looks like in two reference frames. Okay, so I think we can, not everyone will agree in the amount or the way we do true polar wonder. I think it's simple, easy, and we should have no problem with it. And if you do that, you can actually make an absolute reference frame back to Pangea formation, but that's a tiny period of Earth history. It's only 7% of Earth history. So what we really tried over the last year is to something we can go beyond 320, and then this is where the deep mantle comes in, and this is controversial also. Not everyone agrees with what I'm going to show you now. If you look at the core mantle boundary at about 2,800 kilometers here, you see these well-known, they used to be called large, low shear velocity provinces. Kevin Burke simply called them Tucson and Jason, the antipodal. These are thermochemical piles. They have about 3–4% lower shear velocities in the middle. And we know all the subduction for the last 300 million years or so is more or less happening in the blue in the subduction graveyard. And I'm going to show you now, if I just reconstruct now using a global, going back to 83.5 million years, if I reconstruct the large igneous provinces, the centers, you can see every one of them except one, which is the Columbia River basalt, is one of the smallest and the youngest. They are pretty much on the margin. So what I would say from that is that means these thermochemical piles in the low mantle has been stable for at least 83.5 million years. If I now go to the Pacific, you need, I didn't say that, but in the Pacific, there's no way of doing a reference frame for the Pacific before 150. You can do a fixed hotspot back to about 145 or which is the Shetsky rise, and if you also reconstruct those, they're also reasonably on the margin of the other one, which we call Jason. And if you now use Paleomag true polar wonder corrected in different colors, you can see the same scheme here, and I think this would all the way, the oldest one here is called Sklip, sitting in there, 297 million years. So here you see all the large igneous provinces reconstructed for the last 300 million years, show a relation to present-day thermochemical piles in the mantle, and that tells you these must have been stable for so long. But the Columbia River basalt, so 95% of all igneous provinces fall in this pattern. But this is also controversial. Some people don't like this stability, mostly modelers. So I've told you that. So seeing this shows that there is stability for that time. And the question now, can we use this pattern actually to reconstruct continents before Pangea? And its longitude. We will then use Paleomag, and we will constrain longitude by making sure that large igneous provinces, but also kimberlites, we know we have a similar pattern. Not 95%, here to insert maybe 85%, but you can see, I cannot really see here, but this Tuso is underneath here, so you see three large igneous provinces here, you see kimberlites, also kimberlites on here, and they show the same pattern. They are produced by deep plumes from the core mantle boundary on the border of these thermochemical piles. So we will use kimberlites and large igneous provinces. So this is what Kevin Burke will say, this is my planet. It's degree 2 Earth with these antipodal. Also most of the mantle above them are warmer than average to explain the geoid. And we have large igneous province, kimberlites coming from the margins. And the question is, can almost, like diamond software, you can ask yourself, are LLSVPs or are Tuso and JSON forever? So we made reconstruction before using this where we calibrated this whole thing. We also have to use an interactive approach for true polar wonder. And now we can actually make quantity model all the way back to 540. In this case, these are Paleomag reconstructions. And actually the grid is now the mantle frame. So you can see how much they can vary through time. But since we have very strict people throwing me out soon now, I should move on. But I just want to show you, there isn't that many large igneous provinces between 510 and 300, but if I then reconstruct them now, and of course I forced them more or less to be on, but you can now see some of these green here on here. So now, this pattern we could see for 320 million years, there was one anomaly, and then I used this pattern to calibrate continents in longitude, and we can actually have an absolute planet for the last 541 million years. This is all coming out of the Indo-Atlantic reference frame, and of course the opening of the Atlantic, mostly passive margin. And one of the big trouble, if you're going to test this, so a lot of modeling attempts, can you really have this stability? Of course it depends on what kind of parameter, but even more worrying is what is the reference frame, because to test it, you really need information from the oceans. At 200 million years, for instance, the Pacific or Pantalassa was 50% of planet Earth. We have no reference frame. It's totally made up. I've been involved in making it up, but they also means you make up the geometry of subduction sound, which you need for your forward modeling to actually test these things. So from a modeling point of view, it's very, very hard. Of course, there are some problems in these things, and I'll show you now. We made, we can now make a global, so it's the first time I ever show it to anyone. This is a global polar wonder path from 540 to present day. So we used to do it back to Pangaea, because when I use these kimberlites and lips to calibrate my longitude, I also get the relative parameters, so I can then make a polar wonder path for the whole time. And 2 minutes, that's fine. We also calculated true polar wonder through time. This is made in a simple way. It's simply showing what is the deviation from the spin axis compared to today. So there's 0 here, and it's actually oscillating on a point which is about 22 degrees there. And for those who follow this literature, that's an interesting value, because we think the way that what makes the planet stable is these two thermochemical piles, Tucson and Jason. They have the low geos, this stable part of the planet, and true polar wonder is perturbation by subduction. If we lived on a planet without subduction and simply calculate where would the North Pole be, if you only have these piles, that would be somewhere in Russia, and it would be 22 degrees off where the pole is today. So that's why we have some confidence in these calculations. Of course, we can then correct these true polar wonder paths for this, and what you see then for the last 300 or whatever, for here are some wiggles, 3 of them. You can see it gets very smoothed out and nice for the last 300 million years, but you still have some cusps in the older part. And that could be important, because one of the problems now, if the last 540 million years, we've known this for a long time, how you try to make a model, you get very high plate velocities in the early part, also high net rotation, was plate tectonic, two ways of looking, was plate tectonics faster, more action going on, or is it an artifact of our methods? And one artifact could be that we actually underestimated true polar wonder, because when we corrected this global, it goes quite nice and smooth for the last since Pangaea, but you still have these very characteristic cusps. So it could be that we have underestimated. And now, yes, wrap it up. And net rotation is not a problem, because this model we haven't really looked, that's the if there is a discoupling between the mantle and the lithosphere, these oceans are all made up. It's 70% of the planet. We can easily change the geometry to lower the net rotation. And this is my final slide. I would just want to acknowledge maybe my most important worker over the last 15 years, who sadly passed away this year. So that's it.
Thank you. We are sorry, but we have no time for questions. If you use the platform, you can submit the questions.